Okay, this video is going to review section 7.4, which is a big E&M review section, but it's got some really cool applications to molecular dynamics in cells, because charges, Coulomb's law, is one of the biggest forces. I'd say it is the biggest force that governs molecular function, protein folding, and pretty much everything at a cellular level. So prior to this, we've been talking about things without electrostatic interactions. We've been focusing on entropic interactions, so diffusion alone. So we're going to now talk about electrostatic interactions and then see some connections with how that can compete with or work with diffusion in molecular interactions. So to start, let's do a little review of electrostatics. Okay, so what I've got here is a couple of charges. So we have let's just say they're positive just for ease, but they could be negative, they could be one positive, one negative. But what's important, as we remember from Coulomb's law, is that the force between charges depends on the size of the charges and the distance between them. And if we think about energy instead of forces, we are reminded that the potential energy between these two charges, because it's an interaction energy, is K, where K is this Coulomb constant, which is really better expressed as 1 over 4 pi epsilon 0, which we'll see later on in this video. The product of the charges and divided by just one factor of R. And everything but one of the charges we could call V, the potential. It would be the potential created at the spot of Q2 from Q1, and it interacts with Q2 to get a potential energy between the two charges. Okay, so the way potential energy, the way this was derived back in an earlier physics class, is to think about how much work would I have to do to bring Q2 close to Q1, or to a distance of R from Q1, having brought it in from infinity where the interaction is pretty much zero. So to think of that more generally, what we can do is we say, let's consider how much we're going to change, how much does the potential energy change if we bring in a small bit of charge across some potential difference. Okay, so from infinity to near a charge or something like that. So the thing that's going to be most useful is remembering the definition of capacitance. Okay, capacitance, which I've got this as a C with a little tick there. Okay, and I'll use it throughout here just to emphasize we're not talking about concentration. Okay, so I got the C with a little tick. It looks like I wasn't consistent, so let me clean that up a bit. I'm going to put that little tick there. That's the last I'll use it, so that if a normal C will be a concentration. But this is capacitance. And capacitance is defined as the charge on something. It could be multiple somethings, like a parallel plate capacitor would be 2 plates, but you can have a capacitance of a single object as long as it is has size. So you can't have a capacitance of a point charge, but you could have a capacitance of a sphere or a long rod or something like that, where you have multiple charges interacting. Okay, and so if you have all the charges of that thing and the potential at the surface of that thing, then that's the ratio is defined as capacitance. So with that in mind, we can say, well, let's say with V at infinity is 0, then delta V is just V, and rearranging this, plugging in for delta V, we get our little bit of change in potential energy is equal to how much charges are there, and divided by its capacitance, and then multiply that by the change in Q that we're adding. So with that as our now general form, we can integrate both sides to find the total potential, assuming the total potential energy, assuming the potential energy at infinity is 0, because they shouldn't interact much at all. Okay, and then we get just the integral of 0 until we can add it up to its full charge of Q dq, and that the integral of that brings us a 1/2 Q squared divided by capacitance. Again, using this definition for capacitance, only now we have a full charge Q. We end up with 1/2 Q times V. So the potential energy of a macroscopic system So not a point charge, but a macroscopic, something with extent, something with size, is equal to 1/2 times the amount of charge on that thing times the potential at its surface. So we're going to use this idea to try and understand how are macromolecules charged. Now generally, stuff's neutral. And in fact, most stuff that we think of, like my skin, is neutral. I could even look at an entire cell and it's pretty neutral. But when you get down to molecule size, or macromolecules like DNA, they are charged. And so it's like, how did they get charged? Why isn't the Coulomb force dominating and pulling all the ions together to neutralize things? So that's going to be our kind of quest, is to see when is a Coulomb interaction dominant over an entropic or diffusive interaction. So for an example, let's assume I have a droplet of water. This is supposed to be a sphere. I know it's not very pretty, but those 3 circles are supposed to indicate a 3-dimensional sphere of radius r. And let's just ask the question, how much energy would it take for me to just take 1 electron from 1% of the water molecules inside this droplet of water and put it on the surface? Because if I ionize those, they're going to want to get as far away from each other as they can, so they're going to get to the surface of this sphere. Not ionize, dissociate. So if I dissociate one electron. Okay? So we'll define that percent as n. We'll use that a little bit later. So to do so, we're going to need to use our potential energy equals 1/2 Q times V. So we need to find Q and V, V being the potential at the surface. Well, if we look back at or just think about how much charge there is, it's going to be the number that we took off and the size of the charge of the electron. So the number that we took off times the size, and then the voltage at the surface of a sphere, it's as if it's a point charge, but it's got extent, so this radius r. And so this is the total charge. Here's our Coulomb constant, or better yet, 1/4 pi epsilon 0. We'll assume this droplet's in air, and so epsilon 0 will have a size of 8.85 times 10 to the negative 12, as I've listed here, with proper units to make the units in this equation work out. Okay, so and we'll get back to what if we're in water. This constant would change depending on what material you're in. So in air, it's this value here. Okay, so that's from a physics, a first-year physics class. So we take our 2 ideas here, throw it in here, and we end up with this. This would be the potential energy we just created in order to move those molecules, or that number of electrons to the surface of this droplet. So our question is, how big is this if we have a 1 millimeter droplet? And then I'm going to ask the question, well, what if we have a smaller droplet, like a micron-sized droplet? That'd be, kind of a that'd be a cell. Okay, but what about a nanometer-sized object? That'd be more like a macromolecule, a molecule or a macromolecule. So what we need to do is find out how n depends on r. Okay, so remember, this is a sphere, or it's a droplet of water. So how can we find n? All right. Well, we're going to take 1% of all the particles. Okay. So n is going to be the total number of particles, which we can find by doing a ratio of the mass of the droplet divided by the mass of a single molecule of water. Okay, that would be the density of water times the volume of the droplet divided by the mass of a single molecule, which is 18 times the mass of a proton, because that's its atomic mass is 18. Okay, and then n is our percentage, 0.1% of all of that is we're taking out. So that's how we'd find n. So we see that n is proportional to r cubed, but we're squaring it. So this gets kind of ugly here. Oops, sorry. But if we square all this stuff and put it down here, okay, and then we can see what our terms are. We see we have a factor of r below, a factor of r to the 6 above, so that leaves us with r to the 5th. Our percentage is left here squared. And then all the other stuff are constants. Okay? And I did leave off the 0 for epsilon so that we can plug in later on the epsilon for water. Okay? here we will plug in this value since we're assuming this droplet is in air. So with all those constants, okay, then I could calculate a number for it, pretty darn big number. But we see what's important here is it's proportional to the radius of the object to the 5th power, and then whatever percentage we're saying pulls out to the square. And so plugging in 1 millimeter, or 0.001 meters, and 0.01 for our probability, or our percentage, we get 2.2 times 10 to the 11 joules. That's how much energy we would need to put into this thing to be able to dissociate 1%, just 1% of the water molecules. So an electron, to bring in an electron to the surface. Now that's a lot. That is enough power, that's enough energy to power an average American home for 7 years. So clearly, objects even of a millimeter size are neutral because it takes so much energy to try and charge them. It would be pretty much impossible. Okay? So that's kind of the thing to follow from here. First of all, it's a practice with playing with potentials, charges in terms of numbers, and all these other constants. So that's huge. So we conclude large things are neutral. But what about smaller things? So if we have a small molecule, a micron-sized molecule, so not molecule, but a cell, a micron-sized object like a cell, in water this time, and so the permittivity of water is 80 times that in air. So we're just going to change that. We'd end up with a new constant that's similar, okay? But it's still r to the 5th and then this percentage. So plugging in now 1 micron, or 10 to the negative 6 raised to the 5th, we get still a pretty big energy. Not quite that big, but compared to kBt, it's a lot. It's 6.8 times 10 to the 14th times kBt. So even a cell is neutral because there's not enough thermal energy to be able to dissociate molecules from a cell. It's just way too much. But if we get down to the molecular level, where things are on the order of a nanometer or a few nanometers, well, suddenly that energy needed to dissociate 1% of the electrons on the system is about the same size as the thermal energy available. Okay? That's pretty impressive. So there is enough thermal energy to dissociate molecules, which is why we find a lot of molecules, even macromolecules, we find a lot of them charged. So you may have heard that DNA is negatively charged, and most things are actually negatively charged in the system. And so that's because the thermal energy is sufficient to allow the dissociation of an electron. So our question then is, well, where do all those molecules go? So generally we get the negatives stay behind and positive ions leave. Okay? I was speaking in terms of electrons here because that was our model of a droplet of water. But generally your macromolecule, your molecule, we'll think of a strand of DNA, is usually negatively charged because positive sections of the molecule will dissociate away because the thermal energy was able to rip them apart. And so now these want to diffuse, but there's still Coulomb attraction. That positive is attracted to the negatives. All these are attracted to the negative. And so why don't they just collapse back onto it? It's because the thermal energy is, again, sufficient. It's about the same amount. And so though there's an energy that's wanting to bring these back, there's also an energy that's letting these things diffuse. And so what you end up having is you have a concentration profile that is due to a competition between diffusing around and being sucked in. And our question is, what is that concentration profile? If we measure X from the surface of the molecule away from it, what is the concentration? What is that function C of X? And so that's going to be our goal. And we're going to see that's a little bit complicated because we need to find two things at once. We need to find the distribution and the potential. And those are interconnected. But we'll see that with some good math tools we can solve it. Okay, first math tool we need to know, learn, or remember, depending if you've seen it before, is something called Gauss's law. Now, Gauss's law is a pretty slick geometrical law that allows us to find electric fields as functions of charges. And basically the idea is saying that, let's say we have some charge. That's what this red circle is. It's a charged object, it's charged Q. And we'll just say it's positive just for ease. Okay? What Gauss's law says is if you enclose that charge within some pretend shape, and you pick that shape to try and make it as easy as possible to do the math, and I'll explain that in a bit. And if you define, or if that shape has a certain area, now remember, this is not a physical thing. It's just like an imaginary boundary, but a closed boundary that encloses the charge. And if you define outward, normal outward, so perpendicular surface, if you define that to be the direction of the area vector, the whole thing has an area, A, then what Gauss's law says is if you take the component of V that points outward, okay, normal to the surface, that's what the dot product's doing here, is E dot dA says I care about E pointing in the direction of A, and you add up those components times the area over the entire thing, the closed surface. That's what this circle around the integral means. It just means that this integral is a closed integral. It's integrating from the beginning back to the beginning. So on this example, this would be a sphere, a spherical shell enclosing this spherical charge, and I have to integrate over the entire area of that sphere. Okay, so you can't have any openings in your surface. And once you do that, no matter how complicated that integral is, it's equal to how much charge is enclosed divided by this constant. And that's pretty amazing, because this could be pretty darn complicated, but Gauss says it's going to be equal to this no matter what surface is. So you can pick a complicated surface or a simple surface, but if you do that integral correctly, it'll always end up with Q enclosed over this constant epsilon. Okay, now let's test that just to make sure it's clear. And with my little note here, I'm going to use just a regular E for electric field. Just note it's not energy. All the energies we'll talk about in this is going to be potential energy, and I'll use U for that one. Okay, but this is E, not energy in this story. Okay, so let's make sure this makes sense. Let's go up here. We've got let's do it for a point charge. So we know a lot about a point charge. Okay, so if I choose a spherical surface that is centered on that point charge, then E is always going to point radially outward, which means perpendicular to that surface everywhere. So it's constant in both size at the distance r, and it's constant in direction. That's always perpendicular. So since E is always perpendicular to the surface, meaning it's parallel to dA, which also is perpendicular, then the dot product goes away and I just have E times dA. But E, the point charge, is just 1 over 4 pi epsilon 0 times the charge over r squared, which in this case is constant. It's centered on the charge, so r is constant. So it comes out of the integral. So I'm left with just an integral over the surface times a little surface piece, which is just the area of the whole surface, which is a sphere. So I get 4 pi r squared. So I can cancel the 4 pi with this 4 pi, the r squared with this r squared, and I'm left with Q over epsilon 0, the point charge over that constant. So check. Gauss's law gives us something that's familiar. So again, the whole point is that if you integrate over an enclosed surface of the piece of the electric field pointing outward at all places on that surface, you will always get Q enclosed over epsilon 0. Okay, so that is a review or introduction to Gauss's law. We need it in two cases. One, to get what something we also know from a first-year physics class, is the electric field at from the surface of a charged plane. And so you could apply this by choosing the correct surface that works well, but the end result is that the electric field at the surface here is equal to the surface charge density, that's what this symbol is using, sigma sub q, that is the surface charge density, divided by the constant. And since we're going to assume in water, I'll just leave the epsilon 0 off. And or the 0 off, and this is the epsilon, whatever it is for water, so 80 times epsilon 0. So we could use Gauss's law to get this, but we already know this result, so we're going to hold on to it. So just remember that the electric field at the surface is sigma q over epsilon. Now the one we don't know is we want to know what the electric field is through a system out here where all these positive charges are floating around, diffusing around, but also pulled backwards by this attractive force. Okay, and there's going to be some charge density. Now this will be a volume charge density. So our goal is to apply Coulomb's law to this system to try and understand the electric field at a distance x. Okay, the first thing we do know is that charges are going to be pulled to this. Okay, and so there's charges that are in between here and here, and so this face, it feels this negative charge, and there is a net electric field inward because some of these charges are out here which push against it, whereas there's not enough positive charges here to totally compensate for this because of these ones. And so there's a small net electric field pointing inward. Here it's even bigger because more of the charges are on the other side. And so we do have a net electric field pointing towards this negative plate. And so that's going to be how we start. Okay, let's get quantitative now. Let's pick that surface. It's going to be a cube. And this, I've only drawn it in 2 dimensions. So I've got x going this direction, y would go up, and z would come out at us. And so this is a cube or a box of side lengths dx, dy, and dz. Now we're just looking at dx and dy. So dz goes into the page, and dz times dy is equal to the area, or the dA. Okay. Now the electric field's only pointing in the negative x direction because of our symmetry of this problem. It's only pointing in the negative x direction. Okay. So there is no electric field pointing through this surface or this surface on top or this front face or the back face. And so E dot dA on those faces are all 0. So the only faces I care about is this face, this rightward face, and this leftward face. Okay, and the rightward face, the field is smaller, okay, and its points in the negative x direction, but the dA points out of the surface, which means pointing in the positive x direction. So at this location of x plus 1/2 dx, so if x is the center of this, then, and this length is dx, that means this side is x plus 1/2 dx. So the electric field at x plus 1/2 dx, okay, is pointing opposite dA, which means the dot product gives me a minus sign. And then here I have times the area, which was dy dz. Okay, now on this face, they're pointing in the same direction, the electric field and the area vector point in the same direction, so I get a positive electric field at that position, x minus 1/2 dx, also times the area, which is dy dz. So that is the result, okay, that is the result of integrating over this whole surface. Most of the sides gave 0, and then the remaining 2 sides had a constant field times the area of those sides. Now Gauss says that that's equal to the charge enclosed, which we can write as the charge density, the volume charge density. So we have rho q represents the volume charge density times the volume, dx, dy, dz. So if I take a volume density times volume, I get how much is there. This represents q enclosed, how much q is enclosed. And by Gauss's law, I divide by this constant. Okay. Now, we've seen this before multiple times, but if you look at this, we've got the E sorry, let me pause a second. Okay, so we have our form of our derivative. I was getting a little caught because of the minus sign, but I was remembering usually we do the x plus minus the x minus. So if our x is going out this way, so our dx would be this way, but we're doing this minus this one, okay, and so what we're looking for is the magnitude of those two, and what's important is it gets smaller as you go outward. The electric fields are getting smaller as you go outward, and the density is getting smaller as you go out there. So this charge density is getting smaller, and so they're going to scale directly to each other. They should get smaller with distance outward. Okay, so the minus sign disappears when we turn this derivative, because technically our dx is going to be negative as we do it, because we need to go in the direction that we're doing the subtraction. So I know that's a little bit confusing, but the main result is when we take this small change in the value divided by this small dx, which in this case this is negative because we're going in the direction of our change, okay, then we get a dE dx, that's the definition of the derivative. And then if we divide by the dy dz on both sides as well, because they're on both sides, we cancel these out from these ones, and we're just left with the bulk charge density, or the volume charge density, divided by the constant. So this is Gauss's law in bulk. Okay, so in a volume as opposed to a surface. Okay. Now, something that's really powerful is, again, back to a first-year physics class, is the electric field along a direction, let's say x, is equal to the negative derivative of the potential, the electric potential in that direction. And so if we take this and plug it in for E, then we end up with this very important equation that tells us how potential is related to that density. And potential is a lot easier to work with. You can measure potentials by putting in little probes. Electric field's a lot harder to deal with. But we can now measure the potential as a function of this charge density. And this equation is called the Poisson equation. Okay? So our next goal, and this is a lot of steps, this is a lot of math, so be patient as you go through this. It'll take some time to make it all clear, and I hope you're focusing on the main steps, main ideas. What tools are we using to try and solve this? Okay, remember, our end goal is to try and figure out how the potential scales with distance, how the charge density scales with distance, which itself would be telling us how the concentration scales with distance away from a charged surface. Okay, that's kind of our goal. So now that we have this equation, we're going to want to try and solve it. Okay, so first thing to do, let's go ahead and figure out how we can, what can we do with this density equation. Right, so that's going to be where we're going to go next. So with this one, this is the charge density. Now by the Boltzmann factors, we know that the charge density should be equal to the concentration multiplied by the charge on each of those, which will assume everything is monovalent or singly charged. But we know by Boltzmann that concentration ought to be proportional to a Boltzmann factor of the energy over kBt. Remember, it's the diffusive energy, the thermal energy, that's allowing it to diffuse away. But it depends on how strong that attractive force is, which would be that potential energy associated with that potential energy, which is given here by the charge times the potential. So this is our relationship. This is what we have for PQ, but it depends on V. And so we end up with plugging this whole thing in for the charge density. We have a differential equation for potential. And it's pretty ugly. So remember, plug this whole thing right there. We have the second derivative of the potential with respect to x equals the negative of this whole thing, which includes an e to the negative potential over this constant. So it's pretty ugly. So our goal is to solve that differential equation, and so we need to do so with some mathematical tools to keep things clean. And the first thing is to do some substitutions to make it look a lot prettier. Okay, so we're going to define a unitless voltage. That's V bar. And that's simply by taking everything up here and calling it V bar. Okay? Because we know this is an energy, this is an energy, so this is unitless, and as it should be in an exponent. So this is unitless, and it's basically the potential energy, the electric potential energy, divided by the thermal energy, which means we would replace V with this term right here, kBt over the charge of the electron, or the fundamental charge, times this V bar. So we take that and we plug it in right there. Then let's do a dimensionless length, a dimensionless position. And so if we say x bar is equal to x times this whole thing, you're like, well, where did that whole thing come from? Well, I'm kind of skipping a couple steps. If you look at equation 722 in the text, you'll see how by plugging this in first, it causes to bring out a handful of constants. Okay? And these are those constants. We're trying to just make it all simplified. But what's interesting about all these constants is that this whole thing right here within the square root has a unit of inverse length. So if we rewrite it and say, well, just flip this to the other side and invert it, x over here will replace with this stuff times x bar. X bar is unitless. This has units of length, which we're going to see has a very important interpretation. Okay, so if you do all your units on this, you'll find that this has units of meters. Okay, so we'll use that later on. Okay, but to get there, we now have these two substitutions. We're going to take V, replace it with this, take X, replace it with this, and plug them into here with this equation already up here for P, or for the density. So down here, this stuff equaling this stuff, we replace V and X as said with these things, and you'll see a lot of stuff cancels out, and we're left just with this. Okay, just with this out front. Or sorry, I take that back. We can see that all this stuff cancels, leaving the same thing as what's over here. Okay, we have KBTs cancel, those are gone. We have the C naught in the denominator of the denominator, so that's in the numerator, just like here. We have an E squared in the denominator of the denominator, which makes it in the numerator, but we have an E in the denominator of the numerator, so we have one factor of E in the numerator, that's right there. And then we have this epsilon 0 by itself in the denominator, so we have that. So this whole stuff equals this stuff, and they cancel out. Okay, so please, I ask you to take the time to do that math yourself. Do the steps. Make it work. Don't just say, I'm confused, Dr. Hale. Start from here. Take these two substitutions, plug them in here, and show that these things are correct with all this canceling with all this. Okay, so take the time to do that so it makes sense to you. Okay, so with that, we now are left with just this term, just this part, equaling just this part, because all the constants canceled out with our two substitutions. Now that looks like it's something easier to deal with. Okay, now it's still not super easy, but what we can do is we can use some maybe differential equation tricks, but one very legit differential trick is just to guess the solution. And there's some wisdom to this solution, which I'll explain in a little bit. But the author proposes this solution, saying, let's suppose that this function that we're trying to find, a function of x, is equal to a constant times the natural log of a sum, okay, with another constant in there. So we need to check that. So it's a guess and check method. So we take the derivative of this function with respect to x bar, which is right there, and we're going to get this. We get 1 over, because that's the derivative of natural log, and then will be an extra factor of beta will come out because of the chain rule. So we have alpha times beta over 1 plus beta x bar. Take the derivative of that with respect to x to get our double derivative. Well, it's in a denominator. This whole thing's in a denominator, so a negative 1 will come in, and that denominator will be raised to the second power. But we also have chain rule, another factor of beta comes out. So now we have this. And the question is, if this equals this part, and this equals this part, then does this equal this? If this guess was correct, then we should be able to pick constants alpha and beta so that this equation works. So let's take this piece over here, and let's see what it looks like substituting this guess in. So here we have negative e to the negative v bar equals negative e to the negative alpha natural log of the quantity 1 plus beta x bar. Well, that's the same thing as 1 over, so because that minus sign, that's the same thing as 1 over e to the positive that stuff, and alpha in front of the natural log is the same thing as being an exponent on the argument here. And now we can see e to the natural log of that stuff, the e cancels the natural log, and we're left with just this right here. So we have negative 1 over the leftover stuff there. Okay. Again, if you're confused, I want you to go think about how exponentials and logarithms work. Remember how they work. They're opposite of each other. They act opposite of each other. So now what we're saying, now that we've kind of simplified this with this guess, and we've done this with this guess, now we're saying, is this thing here the same thing as this thing here? And you can see, well, at least looks awfully close. And it would be the same if we can find constants alpha and beta such that alpha beta squared equals 1. That's the numerator here equaling the numerator here. And we have 2 equals alpha. So we know alpha equals 2, which would mean it will work if beta equals 1 over the square root of 2. So this was another math tool, the guess and check method of differential equations. Okay, and again, I'll give some motivation why this equation seems works, or is a reasonable one to guess. All right, so moving on, we now can plug those substitutions in, and we have our function. It's a unitless function, which we need to be careful to interpret, but we have that it is equal to 2 times the natural log of 1 plus 1 over the square root of x bar. And we need to think about this in terms of boundary conditions. So we're close. We just need to make sure it's fitting our boundary conditions. The first one is, where is V0? Now remember, V0 is your choice. You can pick V0 wherever you want, but this one's telling us it's somewhere. Because if I plug in x equals 0, I get natural log of 1. And natural log of 1 is 0, so that means at x equals 0, the potential is 0. Now that's fine. We just need to know that we're picking the surface of the macromolecule, or that charged wall. We're picking that to be our origin or our 0 of potential, which would be the same thing as our 0 of potential energy. And that seems like a fine choice, and we'll use that as our convention. Remember, it's just convention, so there's no real physics meaning to that. Okay, but the other one is, well, the electric field ought to go to 0 far, far away. Okay, I need to be careful here. This statement here is inaccurate. It's just the electric field goes to 0. The potential can grow. It just levels out. What I meant to say is not that the potential goes to 0, but it goes to a constant far, far away, because we've picked our 0 at the plate. But the electric field ought to go to 0 far, far away, because you're getting outside of the positive charges, so there are as many positive charges as negative charges, so the electric field ought to go to 0. Now, if that's true, then we want this to be able to go to 0, the derivative of this to go to 0, because the electric field is the derivative of the potential. And indeed, if you take the derivative of this, you're going to get 1 over this quantity here, and when x goes to infinity, this will go to 0. So this is consistent. So this matches our boundary conditions. 1 by convention, 0 at 0, and then the electric field, or its derivative, at infinity is 0. Okay, so that's what we want. Okay, so with that, this is pretty nice. We did a lot of work to get to it, but the question, the only thing that remains, if we look back at our substitutions, remember this is where the physics kind of stop. We have these substitutions right here, this one and this one. Okay, well, we know everything in there, KBT, E, this epsilon, except for this concentration constant. Okay, we need to know what that is. If we can figure out what that is, then we're done. We have solved this entire profile. So how are we going to find that? Okay. Well, the thing we haven't used yet is our knowledge of the electric field at the surface. We know that it is sigma q over epsilon, sigma q being the charge at the surface, so the negative charges. Okay, so if we take the derivative of v with respect to x and evaluate it at the surface, that's what this bar means, is we evaluate this integral at the surface, then we should be able to get the electric field, which is this. But I already know that the voltage is going to be dependent on the constants that we are hidden in these two variables. So it should pull out. So let's go ahead and get this equation now to have the normal v and the normal x and see what we can do with it to find out. So first of all, remember, v equals kBt over E times v bar. Okay, and x equals all this stuff times x bar. Now, just for brevity for a second, I'm going to just leave this and call this a length. I can call it L. Okay, so that x equals L x bar. But then we'll dig into L so we can find out what C0 is. Okay, so our question is take dV dx. If we take dV dx, we're going to see that we're going to get kBt over EL, so this is just L, and then dV bar over dx bar. Okay, so we just have to take the derivative of this with respect to x bar. So let's see what that is. Okay, so we have those constants left out front, and derivative of this, remember we're evaluating it at 0, because that's how we know it's associated with that sigma. So taking the derivative of that function, we get this. Plugging in x bar equals 0 means we're just left with a square root of 2, 2 over square root of 2. Okay, so that leaves us the square root of 2 times the stuff, and that equals, by our surface electric field definition, sigma q over epsilon. Okay, so let's solve for this L because I know that's where the concentration is. So I basically multiply this L up here, and I divide by the sigma q and multiply by the epsilon. So I have all the other constants on this one side equals L. And now I open up L and see what it is, and I have to solve for this. And so I'll let you do that math. You square both sides and solve for the C0. When you're done, you're left with all this. Okay? Sorry about that. So we know C0 is equal to the surface charge density squared over twice the thermal energy times this epsilon constant. Okay? So that is now our value, and that's what we needed. We now have all the pieces, but it's still not terribly clean. So let's do something. Now that I know what C0 is, let's plug it into here and get a cleaner version for L. So that's what we do here, because L is going to be a really nice tool to use. L is some characteristic length. So we just take this, plug it in here, simplify the whole shebang, and we end up with this. It doesn't look terribly nice. Okay, but we do know it's still a length measurement. Okay, let's see how we can go further with it. Okay, so knowing, as we've got our definitions, let's get this back now from our V bar and X bar to our actual V and our actual X by making these substitutions back, and we have this equation here. Okay, now this looks fine, it's not too hard. But if this is a potential and this is a natural log, this is unitless, which means this must be a potential. So I can just call that V0. Okay, it's not necessarily V at 0. It's just, I'll just call that V0. Okay, so we'll say Vx equals V0 times the natural log of this stuff. Now this should be unitless, and it is because it's x over L. Those are both lengths, and I have the square root of 2. Well, that just kind of looks ugly. And since L is a bunch of stuff anyway, let's just bring that square root of 2 in. And so you can see if I go back, this is what it was before. If I am just multiplying that square root of 2 by another square root of 2, I just now have a 2. And so now with a redefinition, we can say that this L times the square root of 2 is just x0. Okay, with that, we have x0 because of the 2 times all that other stuff. And this is now our equation for the potential as a function of distance from the wall, the negative wall. And it's pretty simple. It's not too bad at all. And we have some interpretations for this potential here. It is the thermal energy, twice the thermal energy per charge. Okay, that's useful to know. There's about twice as much thermal energy available per charge for all of this to happen. That tells us that there's enough thermal energy for this diffusive behavior. And this x0 tells us about how far out this effect is. Okay, and that's often called the Gouy-Chapman layer. It's kind of about how thick that wall is. How thick is the cloud that's extending out? And so something that's important here is it tells us that that charge, that concentration of charges, it doesn't go out forever. It decreases pretty quick, and we can see that because remembering before our concentration was whatever initial e to the negative v bar, and now that we know what v bar is, okay, we can plug that in terms of this x and x0, and we get this equation here. And so we see that the concentration decreases pretty darn quick, okay? And x0 is kind of this characteristic length, about how long or how thick is the cloud away from the charged molecule. And it's a shielding or screening length. Okay, so now we've been able to find this concentration with knowing what this constant means. Okay, and we're basically done, but we can do one more thing. I'm going to just do one more thing. Is if this is the concentration, then if I integrate over that for all distances from the wall, I should get all the charge. But all that charge came from the macromolecule, which means it should have the same amount of charge as the macromolecule, just opposite sign. Okay? And so if I think about it, if I say the total amount of charge is going to be equal to this concentration times the volume, which means I'll have to integrate an x and then multiply by the area. So instead, I'll just divide this by the area. So this would be the total charge surface density if I took a huge slab. Okay, and when I do that, if I integrate this function, I get all these constants come out. And what's interesting here is if you look at this, pull just one of these sigma q's out, everything that's left over is 1 over x0. If you look back at the notes, that's the same as x0, 1 over x0. So this whole thing right here is just sigma q over x0. And when you do this whole integral with what's left over, this 1 plus x over x0 to the negative 2, or 1 over it squared, if you do that whole thing, evaluate it from 0 to infinity, you just get x0. I'll let you again do that math to show that, to get confidence in that. And so the x0's cancel, and we're just left with sigma q. And that's what we should get, because the positive charges for the bulk, for the cloud, divided by the area, is a surface charge density of the positives. And it should be equal to the surface charge density of the negative, because that's where they came from. So we can put a big check here saying that this is consistent with everything we've done. We've now been able to determine this cloud behavior, the geometry of it, and its distribution. And it also tells us a lot of things about how molecules will interact with each other. Because if you're outside this x0, if you're beyond this x0, then it's pretty much neutral. And that's why there's not a lot of clumping that happens inside cells, because it's pretty much neutral. Okay, but if you start getting things pushed closer together, so you start to enter this cloud or get closer than x0, then you start to feel an electrostatic signature. And you can get attraction or repulsion, depending on what the two charges are. Generally, it's attraction as you get these profiles of molecules, and that's how proteins fold, is they get these specific charge patterns that match both by charge and by geometry. And so, though in the bulk level, things look pretty neutral, on very close up, things start to get electrostatically dominant. And so electrostatics dominate on very short levels, whereas diffusion dominates on very long levels. Okay, that was a lot of math. And again, this is supposed to help you read the text so it makes more sense, so you can see that. And then I encourage you to read the text and to do some of those steps. Follow these steps, do them in your own work to make sure things are clear. And we'll try and answer any questions in class.